Hi everyone, my name is André and I'm here to present my work, Three-Phase Quaternion Power in Three-Wire Systems. A framework based on quaternion seems to be promised for analysis of several problems in power systems, and has already produced some interesting results. In this work, we studied the quaternion power for a general load in delta configuration. We will be analyzing a balanced load and an unbalanced load. Quaternions can be defined as described in this equation, where r, x, y, and z are real numbers, q1, q2, and q3 are basic quaternions, and 4, along with 1, the orthonormal basis of the hypercomplex space. The product of two quaternions is non-commutative. This table represents the product of basic quaternions. The product of q1 if q2, for example, is q3, but the product of q2 with q1 is minus q3. All the other combinations can be observed in the table. Final balance voltage can be defined by this equation, where VA, VB, and VC are balanced voltages in time domain. Analogously, the three-phase current quaternion is defined by this equation, where IA, IB, and IC are line currents flowing through phases A, B, and C, respectively. The power quaternion is defined by the product of the tension quaternion with the conjugated of the current quaternion. Now I will be presenting the quaternion power of a three-phase balanced delta load, described by its phase-to-phase admittances. The quaternion power of the balanced delta load is defined by this equation, where n is a unitary quaternion. The expression of the quaternion power is equivalent to the expression obtained for the complex power of this load, changing the imaginary unit j for the unitary quaternion n. Now we will be analyzing a three-phase unbalanced delta load, defined by its phase-to-phase admittance as well. The power quaternion of this load can be written as this equation, where the varying time terms are described here. Comparing the quaternion power to the usual complex power, it can be observed that the first three terms are equivalent to the complex power, substituting j for n. The last three terms are unique to the quaternion power representation and account for instantaneous power dynamics. Summing the three constant terms will obtain this constant quaternion, and also summing the three varying time terms will obtain this varying time quaternion. So, we can rewrite the quaternion power as this equation. The first term represents the quaternion power of the average of the admittance between each phase. We can observe that it is analogous to the balance case. Term is the quaternion power of the association of these two loads. These loads have no average power, so the average power of the quaternion power is concentrated on the constant term. Returning to the quaternion power expression, we can sum these terms, obtaining this expression for the quaternion power. The expression is analogous to the balance case, implying that the three-phase unbalanced impedance can be represented by a three-phase balanced load, with modulus and phase varying time. Conclusions. The quaternion power can be expressed with two terms, a constant term, equivalent to the usual complex power, and a time-variant term that accounts for the contribution of load unbalance on the power. This second term can be used as a measure of the load unbalance level, since y omega is constant. An unbalanced delta load can be decomposed in terms of a balanced load and an unbalanced load with no average power. This unbalanced load can be obtained by the association of these three loads. An unbalanced delta load can be represented as a time-varying balanced load, as we observed from the last equation of this work. These are the references. Thank you for your attention, and if you have any doubts, I will be glad to answer.